These are the book problems, acids and bases. I'm going to take my time with the first bunch of slides and then decrease the amount of time as the movie goes on. Identify the Lewis acid and Lewis base in each reaction. Well, the first one, the hydrogen needs to accept electrons, so that will make it an acid, and the water will donate, that will make it a base. The next one, the chlorine will donate electrons, so that will be the base, and then the aluminum chloride will accept them. That will be the acid. So H plus is the Lewis acid, water is the Lewis base. That's what I said, and you'll see that the aluminum chloride, which has no excess electrons around the central atom, will, as a result, accept electrons. It has no choice. It has none to donate. So it will actually accept electrons, and the chlorine will donate its extra electron, which makes it an even pair. So that will be the Lewis base. So where the Brønsted-Lowry is an acid, is a proton donor, and the base is the proton acceptor, it's the reverse with the Lewis acid base, where Lewis, the electron donor, is the base, and the electron acceptor is the acid. Would you predict phosphorus trichloride to be a Lewis acid or a Lewis base in typical reactions? Explain your prediction. A Lewis base, it has a non-bonding pair of electrons that it can donate. So molecular geometry is important in this chapter. What are the properties of acids and bases? Well, they're both corrosive. Both are electrolytes and change the color of an acid-base indicator. Acids have a sour taste, bases have a bitter taste. How did Arrhenius define an acid and a base? An acid gives a proton or hydrogen ions in solution, and a base gives a base gives hydroxide ions in solution. How are acids and bases defined by the Brønsted-Lowry theory of acids and bases? Acids are hydrogen ion donors, and bases are hydrogen ion acceptors. What is the Lewis theory of acids and bases? Well, the acid, a Lewis acid, is an electron pair acceptor. A Lewis base is an electron pair donor. Number 7a, what is a conjugate acid-base pair? Well, a conjugate, two substances related by the loss or gain of a single hydrogen ion. I'll explain later more. Write equations for the ionization of nitric acid in water and the reaction of carbonate with water. For each equation, identify the hydrogen ion donor, the hydrogen ion acceptor, then label the conjugate acid-base pairs in each equation. There's the equation. The acid is the hydrogen ion donor, and its conjugate base is the nitrate ion, -1 charge, and water is the hydrogen ion acceptor. Water is the hydrogen ion acceptor, and the hydronium ion is the conjugate acid to the hydrogen ion acceptor. Write equations for the ionization of nitric acid in water. This is the same problem. Then label. So you have carbonate plus water yields bicarbonate plus hydroxide. The carbonate is the hydrogen ion acceptor because you're getting the bicarbonate, and the conjugate acid is the bicarbonate because you're creating the bicarbonate, and then water is the hydrogen ion donor because that's giving the carbonate the hydrogen ion, and then its conjugate base is the hydroxide ion. Identify the following acids as monoprotic, diprotic, or triprotic. Explain your reasoning. Diprotic, because two hydrogens, that's carbonic acid, that's diprotic, two ionizable hydrogens. Triprotic would be like phosphoric acid, for instance. That's exactly what it is. Triprotic would be three ionizable hydrogens. And then monoprotic would be hydrochloric acid, for instance. That would be monoprotic. There it is. Pyrophosphoric acid would be H4P2O7. That would be tetraprotic. And the HCl would be monoprotic, one ionizable hydrogen. And sulfuric acid is diprotic, obviously. And that's because it has two ionizable hydrogens. Let's see what's left as the plot thickens as we wait. Classify each solution as acidic, basic, or neutral. Again, what causes something to be acidic? The H ion, very small. It's going to be basic. We'll see why that's basic when we do the pH. It has to do with the exponent of the base 10. It's going to be basic. That's going to be basic. That's going to be acidic. That's going to be acidic because the pOH will be -2. It'll be basic. This will become a little clearer later on. It's kind of weird that they're doing this now. That's going to be pretty much neutral, but it will be slightly acidic. Very slightly acidic. Very slightly acidic. 1 times 10 to the -7 is neutral. That's going to be completely neutral. That's 1 times 10 to the -7. That's a pH of 7. So the pH is negative log of the H ion concentration, and the pOH is the negative log of the OH concentration. If the hydroxide ion concentration of an aqueous solution is 1 times 10 to the -3 molar, what is the H ion concentration? Is the solution acidic, basic, or neutral? Well, they have to, if you multiply the two, they have to equal 1 times 10 to the -14. Find the pH of each solution, so it would be the negative log of each solution. So that will be 4, because it's negative log of the H ion concentration. And there's the actual calculation. Now, as I said before, if I take the H ion concentration and multiply it by the OH concentration, that should equal 1 times 10 to the -14. So here is the pH equals the negative log of the H ion concentration, and that's 2.82. What are the pH values of the following solutions based on their hydrogen ion concentration? So that will be 12. So that's very basic. That would be 12. Because if it's 1, and then it's just the exponent, or negative exponent. That's 4.5 times 10 to the -2, so it would be a little less than 2, between 1 and 2, so that's 1.35. It's a pretty serious concentration. That should be H plus, by the way, that's just a typo. Calculate the H plus concentration for each solution. So pH of 5, so it would be 10 to the -5, which would be 1 times 10 to the -5. Okay, so that is actually, the way you calculate that is 10 to the x, where x is the negative pH. So it would be 10 to the negative, 10 to the negative, 10, you're raising each side 10 to the x. What are the hydrogen ion concentrations for solutions with the following pH values? 4. Well, it'd be 1 times 10 to the -4 H ion concentration. Because it's just it's just the exponent. When it's 1, when it's 4.0, it would be 1 times 10 to the -4. That would be, so it would be it would be 10 to the negative 11.55, which is 2.8 times 10 to the negative 12 molar. Number 15, we're going through these rather quickly. Calculate the pH of each solution. So this is just very basic plug and chug stuff. So that would be the pOH would be negative log of the pOH, or you could do Kw divided by OH, and that's going to be the H ion concentration. That would be the negative log of the H ion concentration, which would be 9.63, 9.63. And then this one would be, again, 1 times 10 to the negative 14 divided by that, which would be pretty acidic, actually, if you think about it. Would be pH of around 3.65. Again, if you have any problems with these, stop and see me. Very, very simple stuff. Calculate the pH of each solution. Calculate the pH of each solution. So it would be negative log of 5 times 10 to the negative 5th molar, and that's going to equal 4.30. Again, you just plug and chug. Plug and chug. And then it would be negative log of 8.3 times 10 to the negative 11th. Very basic. And that would be 9.08. Medium basic. And then number 17, what is the relationship between H plus and OH minus in an aqueous solution? There, the product of their concentration should equal 1 times 10 to the negative 14. When H ion concentration in the solution increases, the OH negative has to decrease. What is true about the relative concentration of hydrogen ion and hydroxide ion concentration in each kind of solution? Basic. Well, the hydroxide ion concentration would be greater than the hydrogen ion concentration. If it's going to be acidic, probably the hydrogen ion concentration or hydronium ion concentration would be greater than the hydroxide ion concentration. And if it's neutral, they would be equal. So this is pretty basic stuff. So you guys should be doing very well with these first bunch of questions. It's neutral if they're equal. So after doing some of those buffer problems in the last couple of days, I would suggest going over the acetic acid part 1 through 6. That'd be pretty important on YouTube. What is true about the colors of a pH indicator? The color of the H indicator aqueous must be different than the color for the anion aqueous. Determine the pH of each solution. Again, so it's going to be negative log of 1 times 10 to the negative 6, which would be 6. Easy. When it's 1, then it's going to be the negative exponent. This would be 1 times 10 to the negative 4, which would be 4. That would be the pH. And then 1 times 10 to the negative 2 would be 2 for the pOH, so it would be 12 for the H. Easy. Because it's going to be 1 times 10 to the negative 2 times 1 times 10 to the negative 12 is 1 times 10 to the negative 14. And that would be negative 11, so it would be negative 3, so it would be 3. You should be able to do some of these in your head if you are comfortable with scientific notation. What are the hydroxide ion concentrations for solutions with the following pHs? Again, 14 minus the pOH. 14 minus the pH is the pOH. So that's going to be, and then you raise it to 10 to the x, so that'll be 1 times 10 to the negative 8 molar. 9 would be, you get the pOH would be 5, and then it would be 1 times 10 to the negative 5 would be the concentration of the hydroxide ion concentration. 12 would be 2, so 1 times 10 to the negative 2 molar would be the POH. And then let's see, are we doing anything else here? Is there a D or is it 22? 22. In an exactly 0.1 molar solution of methanoic acid, H plus concentration is 4 times 10 to the negative 3 molar. Calculate the Ka of methanoic acid, and it's going to be 1.8 times 10 to the negative 4. Let's stop here and explain that a little bit before we continue. So the reason this is true is because when the methanoic acid breaks down, it will break down into the H ion concentration plus the anion concentration, and they're going to be equal. They're going to break down 1 to 1. And so it will be 4.2 times 10 to the negative 3 times 4.2 times 10 to the negative 3 divided by 0.1 minus the 4.2 times 10 to the negative 3, because that's going to be the equilibrium concentration. So 0.1 minus 4.2 times 10 to the negative 3 equals 9.58 times 10 to the negative 2. So it'll be 4.2 times 10 to the negative 3 squared divided by 9.58 times 10 to the negative 2, and that's going to equal 1.8 times 10 to the negative 4. That's how you get the kind of weird numbers there. So I think we talked about that a little bit, but very basic stuff. Remember, it's the equilibrium concentration. It's not going to be the original 0.1 because some of the acid has dissociated. In an exactly 0.2 molar solution of monoprotic weak acid, the hydrogen ion concentration is 9.86 times 10 to the negative 4 molar. What is the Ka for this reaction? Well, the H ion concentration is very low, very small, so 0.2 minus 9.86 times 10 to the negative 4 is going to be basically 0.2. So it'll be 9.86 times 10 to the negative 4 squared divided by 0.2 is basically going to be the answer. If the H ion concentration is low enough, you don't really have to subtract it from the 0.2, because in terms of significant figures and precision, it's going to be the same if you subtract from it or not, if you're going to calculate it to 1 or 2 significant figures. So it really doesn't matter all that much. So whether or not they do that here, I don't know, but if your value for the H ion concentration is low enough, or if the Ka is low enough, you don't have to worry about that minus X business. It's not a big deal. So let's see what they come up with here. And that is exactly as I suspected. It's going to be 9.86 times 10 to the negative 4 squared divided by the 0.2. Compare a strong acid and a weak acid in terms of the acid dissociation constant. Strong acid will have a large value and a weak acid will have a small value. A strong acid is completely ionized in aqueous solution and has a large Ka. A weak acid is ionized only slightly in aqueous solution and has a small Ka. So it depends on the amount that's ionized. Remember, it's numerator divided by the denominator. How do you determine the Ka of a weak acid or the Kb of a weak base? Substitute the measured concentrations of all the substances present at equilibrium into the expression for Ka or Kb. Which acid in table 19.6 would you expect to have the lowest ionization constant? The smallest one. Hypochlorous acid. Very weak acid, very weak acid. Often used as a buffer system, but weak acid. Acid HX has a very small value for Ka. How do the relative amounts of H and HX compare at equilibrium? The HX is much greater than the H plus. Much greater. Write the equations for the ionization or dissociation of the following acids and bases in water. Nitric acid, which would be HNO3, yields H plus, and then, or the hydronium ion, if you're going to include water, plus the nitrate ion, -1 charge. And then ethanoic acid, which is really acetic acid. Very annoying that they call it ethanoic acid. So it'd be the ethanoic acid plus water yields the acetate and the hydronium ion concentration. Ammonia would be ammonia plus water yields ammonium plus hydroxide. What else? I think that might be it for 28. Oh, magnesium hydroxide. So it would be magnesium hydroxide, and what? It would yield, sort of has water in already, it would yield magnesium plus 2 and 2 hydroxides. Compare the terms strong, weak, and concentrated dilute as they pertain to acids and bases. Strong acids and bases are completely ionized in aqueous solution. Weak acids and bases ionize only slightly in aqueous solution. Concentrated acid or base solutions contain large amounts, high concentrations of acid or base. Dilute acid or base solutions contain small amounts, low concentrations of acid or base. These early fundamentals are very important, and you'll be able to appreciate them much greater as the material becomes more complex. How many moles of potassium hydroxide are needed to completely neutralize 1.56 moles of phosphoric acid? Well, phosphoric acid is H3PO4. So, how many moles are you going to need? Well, you're going to need 3 times the amount, because you're going to have 1.56 moles of phosphoric acid, which is really, you need 3 times that amount of potassium hydroxide because it's triprotic. So multiplied by 3. How many moles of sodium hydroxide are required to neutralize 0.2 moles of nitric acid? Well, it's going to be 0.2 moles because it's 1-to-1. Easy peasy, because it's 1-to-1. Acid 1-to-1 moles of each. So you're going to need 0.2 moles of sodium hydroxide. The idea of equivalence is very important here. How many milliliters of 0.45 molar HCl will neutralize 25 milliliters of 1 molar potassium hydroxide? Set up a ratio and proportion, and solve for x, 0.025 moles. 0.025 moles. Remember, it's 1-to-1. And then you say, well, set up a new relationship, 0.025 moles over x, solve for x, 56 milliliters. 56 milliliters. 33. What is the molarity of phosphoric acid if 15 milliliters is completely neutralized by 38.5 milliliters of 0.15 molar NaOH? Let's take our time with this one and see if we can come to a better understanding of what it is that is going on. Well, the first thing I want to do is I want to know how many moles of hydroxide actually was used, because it says is completely neutralized by 38.5 milliliters of 0.150 molar sodium hydroxide. So, how many moles of sodium hydroxide were actually used? Because then it would be 1-to-1. If I know the moles of sodium hydroxide, I know the moles of hydroxide. So then I know that, well, wait a second. I have to determine the molarity of the phosphoric acid. Well, if let's say I use 3 moles of sodium hydroxide, that would mean there's only 1 mole of phosphoric acid. So you divide by 3. So let's take this one step at a time and see what we can see. So if I have 0.15 moles of potassium hydroxide, per 1,000 milliliters. That's the molarity. And I know that I used 38 milliliters of that. How many moles? I know how many moles there were in 1,000 milliliters, but how many moles are there in 38.5 milliliters? Now, so I simply set up a proportional relationship, and I will figure out, think about this, I'll figure out how many moles I actually used. How many moles I actually used. So cross multiply and divide, and I come up with 0.0058 moles. Well, that's the amount of moles that neutralized the phosphoric acid. But I didn't have that much phosphoric acid, because if you divide that number by 3, that's how many moles of phosphoric acid I have. Now I know how many moles of phosphoric acid I had. Divide by 3, so it's 0.00193 moles. So I had that many moles per 15 milliliters. Well, if I have that many moles per 15 milliliters, how many moles do I have per 1,000 milliliters? And that will be my molarity. So now I set up another problem, and I say, right, I say 0.00193 divided by 15 equals x over 1,000. Now I'm going to solve that proportional relationship for x, and I will wind up with a number of moles. That number of moles will be over 1,000, so that number of moles will be the same as the equivalent of the molarity. So whatever you get for moles, you can call it the molarity of that solution. So I'll wait for you to finish. Oh, there it is. Well done. 0.129 molar. That's the molarity of the solution of the starting phosphoric acid. What are the products of a reaction between an acid and a base? Strong acid, strong base, especially you get a salt and water. Easy. Or a strong acid and a weak base, same idea, but there are differences. What occurs at the end point of a titration? Neutralization is the end point of titration. Neutralization is the end point of titration. How many moles of HCl are required to neutralize aqueous solutions of these bases? How many moles? 2 moles of ammonia. Let's see, 2 moles of ammonia. So it'll be ammonia plus HCl. It'll be 2 because it's 1 to 1. It's ammonium hydroxide, etc. So it would be 0.1 moles of calcium hydroxide. That's going to be 2 to 1, so it's going to be 0.2 relative to 1 to 1, or 2 to 2 for the ammonia. Write complete balanced equations for the following acid-base reactions. So you're just balancing these. So the first one is going to be 2 potassium hydroxide and 2 HOH. And I'll let you do these and see how you do. See how you do. The first one's pretty easy. Let's see what you do. It's not bad. 2, 3, 1, 6. Those are my coefficients. 2, 3, 1, 6. And 2, 1, 1, 2. Pretty straightforward. Let's see, we'll do a couple more. Write reactions to show what happens when the following occur. Acid is added to a solution of hydrogen phosphate. So hydrogen phosphate, you make an acid that's going to give you dihydrogen phosphate. Base is added to a solution of dihydrogen phosphate. It's going to go back the other way, and because I'm going to deprotonize it, and I'm going to end up with water. Write an equation that shows what happens when acid is added to ethanoic acid ethanoate buffer, or acetate. Okay, so I'm going to make acetic acid. What type of salt produces an acidic solution? a basic solution. Acidic solution, salt of a strong acid and a weak base, for instance. Basic solution, salt of a weak acid and a strong base. Think sodium carbonate. What substances are combined to make a buffer? What substances are combined to make a buffer? A weak acid and one of its salts, or a weak base and one of its salts. In other words, think conjugate acid, conjugate base, etc. Which of these salts would form an acidic aqueous solution? Ammonium sulfates. Ammonium sulfates. Excellent. Using equation, show what happens when acid is added to an ammonium ion ammonia buffer. What happens when the base is added? So this is the addition of the acid. I'm going to make more ammonium, and I do the base, and I'm going to make more ammonia. So that's a buffer system. How did Arrhenius describe acids and bases? How did Arrhenius describe acids and bases? Acids ionized to give hydrogen ions in aqueous solution. Bases ionized to give hydroxide ions in aqueous solution. 45. Classify each compound as an Arrhenius acid or an Arrhenius base. All right, let's see if we can do this together. Arrhenius base, because that's hydroxide. Calcium hydroxide is Arrhenius base. Base. Next. I'm giving 8 seconds for these, kind of long. I hope you said acid. I hope you said acid. What's next? Very slow going. Let's stop this and speed this up a little bit, shall we? That's going to be a base. As I said, that's a base. That's going to be an acid. The next one is going to be an acid. This is only 3 seconds. It seems like forever. That's going to be an acid, obviously, sulfuric acid. And that's it. Okay. Write an equation for the dissociation of each compound in water. All right, here we go. Potassium hydroxide. So it's going to go into K plus 1, OH minus 1. Pretty straightforward. And then it will be magnesium hydroxide is going to go to magnesium plus 2 and 2OH minus. And then you'll go to, number 47, write balanced equations for the reactions of each metal with water. So lithium plus water yields lithium hydroxide plus hydrogen gas. Let's see if that's correct. Yep, lithium plus water yields lithium hydroxide plus hydrogen gas. What's next? Barium. Barium plus water is going to yield barium hydroxide plus hydrogen gas. Not a big deal. Identify each reactant in the following equations as a hydrogen ion donor acid or a hydrogen ion. So the acid will be a red oval and the base will be a blue oval. It's only going to be 3 seconds for each. Let's get going. Okay. That's going to be an acid. That's going to be a base. And then the next one, you're going to have an acid, then a base again. That's the ethanoic acid and the base. And then, let's see, base and then acid. That's the base. Water's the acid. And then acid and base. And that's it. Make sure you can do this as quickly. Try to predict things. Label the conjugate acid-base pairs in each equation in problem 48. All right. So which one's going to be the conjugate acid-base pairs? Okay, here we go. A. You have nitric acid and water, so it'll be the nitric acid with the nitrate and the water with the ammonium. The acidic acid and the acetate and the water and the hydronium. Okay. And then the ammonia and the ammonium and the water and the hydroxide. They're easily related. And then letter D would be the water and the hydroxide and the acetate and the acidic acid. Easy peasy. Okay, I'm going to do one more and then I'm going to quit. I'm half done and I'll finish it in the morning. What is a Lewis acid, a Lewis base? In what sense is the Lewis theory more general than the Arrhenius-Brønsted theories? A Lewis acid accepts a pair of electrons to form a covalent bond. Very big. Lewis base donates a pair of electrons to form a covalent bond. The Lewis theory explains the behavior of compounds that act like bases without accepting hydrogen ions, or that act like acids without donating hydrogen ions. Very interesting, very different from a Brønsted-Lowry or Arrhenius acid and base theory. Write an equation showing the ionization of water. Well, water ionizes to plus H, or the hydronium ion, and hydroxide. They are ionized in equal amounts, 1 times 10 to the negative 7th, 1 times 10 to the negative 7th molar. That's the ionization of water. And the pH of water is 7 because it's 1 times 10 to the negative 7th, and the negative log would be 7. What are the concentrations of the H plus and the OH in pure water at 25 degrees? 1 times 10 to the negative 7th each. They're both equal, and the pH is 7. It's considered neutral. 1 times 10 to the negative 7th molar for both H plus and OH minus at 25 degrees Celsius. If you add any kind of acid or base, it will go up and down depending upon the content. How is the pH of a solution calculated? The pH is the negative log of the H ion, the molar H ion concentration, or the hydronium concentration. The H ion concentration can be either calculated or measured using a pH meter. It can also be relatively tested using pH paper. Why is the pH of pure water at 25 degrees Celsius equal to 7? Because it's the negative log of the molar H ion concentration. Some of these questions are extremely basic. We're better than halfway through so far. I should have changed the timing on some of these problems, but it's relatively straightforward. There has not been anything challenging so far, with the exception of 1 or 2 problems that I expanded the timing for, but these are fairly straightforward. What I'm going to do is I'm going to change the timing on these. The hydrogen ion concentration in pure water is 25 degrees Celsius, and it is 1 times 10 to the negative 7th. The negative logarithm, or pH, of this concentration is 7. When it's 1, see 1 times 10 to the negative 7th, when it's 1 precedes the time sign, then you just take the additive inverse of the exponent. Calculate the pH for the following solutions and indicate whether each solution is acidic or basic. Again, they're all going to be 1 times 10 to whatever. So if it's 1, then you can take the negative of the exponent. So that'll be 2. They'll have a pH of 2. See here it says 1. So if that's a 1, then you can just say 2, the additive inverse of the exponent, or the negative of the exponent. So the next ones are going to be quick. So that one is 2, and then that's going to be 2. Actually, it'll be 12, because it'll be 2, and then 14 minus 2 is 12. That'll be 8. 14 minus 8 is 6. So it'll be 6. And you can see that that's going to be acidic. Okay, what are the hydroxide ion concentrations for the solution of the following? All right, so that's a 4, so that will be 14 minus 4 is 10, and then it'll be 10 will be the one. I mean, it'll be 10 will be the POH, but they're not asking for the POH. They're just asking for the other. So this will be 8. So 14 minus 8 is 6. So it'll be 1 times 10 to the negative 6. And then you'll have 12. 14 minus 12 is 2. 1 times 10 to the negative 2. And then you'll have, let's see, calculate the pH or the H ion concentration for each solution. So you'll simply say negative log on your calculator, put that in, and you get 5.62. Put in 10 to the x, and then put in 13.2, and then that'll be the negative 13.2, and then hit equals, and that will be your value. Identify each compound as a strong or weak acid or base. Strong base because of the OH, very strong base. Sodium hydroxide dissociates completely. That's why it's strong. It's a base because of the OH. HCl is a very strong acid, dissociates completely, and the H plus will make it an acid. So it's a strong dissociation acid because of the H. What's next? Ammonia is a classical weak base. Ammonia is a classical weak base. Got some kind of thing buzzing inside. Be right back. That will be sulfuric acid, and that'll be a strong acid. Strong acid, sulfuric acid, very strong. Very dangerous too. It can cause severe burns, just the fumes of it can. Would a strong acid have a large or a small Ka? Well, the larger the Ka, the stronger the acid. A strong acid is completely dissociated. A Ka must be very large. And why is that? Well, we'll look a little bit later. Why are magnesium hydroxide and calcium hydroxide considered to be strong bases, even though their saturated solutions are only milky basic? They have high Kb values. Their concentration is saturated solution. In saturated solution is low because of their low solubility. Next, write the expression for Ka for each acid. Assume only one hydrogen is ionized. HF, it will be H plus times F minus divided by HF. The molar concentrations of each will be the Ka. So you can see that if it's completely dissociated, the numerator is very large, so the Ka would be large. That's a weak acid. Again, it's only one, so that's all very self-evident. I'm not going to read it to you. So the reason the Ka is large or small is because it's mathematically large or small. Write a general word equation for a neutralization reaction. Acid plus base yields a salt plus water. So it could be a weak base or weak acid. The salt would be either neutral, acidic, or basic. Identify the products and write balanced equations for each neutralization reaction. That's going to be water and potassium nitrate. That's going to be a neutral salt because two strong acids make a neutral salt. That's going to be a calcium chloride and water, considered to be a neutral salt. That's another way of determining whether or not it's a strong base, is to find out whether or not the salt is acidic, or basic. That's going to be another neutral salt. That's sodium sulfate plus water. And then 64, moving right along here. We're only going to 99, so this is going rather quickly. What is characteristic of the endpoint of a titration? Always remember, Endpoint of titration is neutralization, and the indicator color changes. The indicator color changes. What is the molarity of sodium hydroxide if 20 milliliters of a solution is neutralized by each of the following 1 molar solutions? 28 milliliters of HCl. 28 milliliters of HCl would be 1.4 molar. Work it out. Again, ask me questions. I'll be there a little bit, I'll be there during lunch, and you can come up and ask me questions. 17.4 milliliters of phosphoric acid, 2.61 molar. Very straightforward. What else? What kinds of salts hydrolyze water? What kind of salts hydrolyze water? Salts with a cation from a weak base and an anion from a strong acid, or with a cation from a strong base and an anion from a weak acid. So, for instance, sodium carbonate is the salt of a weak acid, so it's going to be basic. The salt of a weak base is acidic. Write an equation showing why an aqueous solution of sodium hydrogen carbonate is basic. That's because it produces an OH. That's why it's basic. Explain why solutions of salt that hydrolyze water do not have a pH of 7, because you have excess OH or H plus as a result. Weak acid ions accept protons from water, increasing the pH of the solution. Weak base cations donate protons to water, decreasing the pH. Predict whether an aqueous solution of each salt will be acidic, basic, or neutral. This is a very good problem. Okay, here we go. That will be basic because it's a salt from a weak acid, so it'll be basic. Excellent problem. Because you'll produce hydroxide ions. Remember, salt of a weak base, salt of a weak acid, whatever the case may be. All right, salt of a weak base, so it will be acidic. Salt of a weak base, because that comes from ammonia, which is a weak base. Next, very good problems. Let's see. Potassium chloride, it'll be neutral because it's from potassium hydroxide and hydrochloric acid, so it'll be neutral. Let's see what's next. That's a good problem. I think that might be it. Oh, here's another one. That will be basic, the carbonate ion. That'll be very basic. So it's going to be, you have the carbonate, which is a salt of weak acid, so you'll form carbonic acid right away. That's the salt of a strong acid, so that'll be neutral. The sulfate will be from sulfuric acid, the H2SO4, so it'll be neutral. That will be acidic because that's from ammonia, so that will be acidic. And I think that's probably it. Yes, a buffered solution cannot absorb an unlimited amount of acid or base. Eventually, the buffer capacity of the buffer is exceeded and the pH will change significantly with the addition of stronger acid or base. Is it possible to have a concentrated weak acid? Well, yeah, you just make it saturated. Yes, acids like acetic acid dissolve well, but ionize poorly. You have, for instance, glacial acetic acid is concentrated. Write equations showing that the hydrogen phosphate ion is amphoteric. In other words, it could be an acid or a base. So that's going to be an acid. That's act like an acid, but then it's also going to want to gain a proton, and that will make it a base. There we go. That makes it a base. Excellent. Acting as a base. Amphoteric means it can be an acid or a base. The pH of a 0.5 molar nitrous acid solution is 1.83. what is the Ka of the acid? All right, excellent. So what we're going to do is we're going to do this problem out more completely. So we know that the negative log of the H ion concentration is 1.83, so we're going to raise both sides to 10 to the x, and then we're going to see what the H ion concentration will be. The H ion concentration and the anion concentration will be the same, so I simply square the H ion concentration, because for each H ion you're going to get a nitrite. So you're going to raise both sides to 10 to the x, and then you will get 10 to the negative 1.83, and that will be the H ion concentration will be 1.48 times 10 to the negative 2. Now that we have the H ion concentration, we can write the formula for the Ka, the ionization constant formula, and we see that we're going to multiply the H ion concentration times the nitrite concentration, and it should be 1 to 1. If you look at the equation will say 1 HNO₂ yields 1 H plus and 1 NO2. So they're going to be equal. So what I'm going to do is I'm going to essentially square the numerator. Now the denominator, let's look at the denominator. Well, the H ion concentration is not that small, actually, relative to the concentration of nitrous acid. Now, let's say the H ion concentration was 1.48 times 10 to the negative 10. Well, subtracting it from the concentration, the initial concentration of the acid, would be unnecessary, because in terms of rounding, you would have a number that is very, very small, and would be, you're subtracting from the 0.5. So it would be unnecessary to bother doing that. So what I'm doing here is, because the H ion concentration exists at equilibrium, I'm going to subtract it from the starting concentration of the nitrous acid. And let's see what happens when I do that. So I can clearly see that it's going to have some effect intuitively. So I say 1.48 times 10 to the negative 2 squared divided by parentheses 0.5 minus 1.48 times 10 to the negative 2 end parentheses divided by, and that's going to be 4.5 times 10 to the negative 4. So the book may say 4.6 times 10 to the negative 4, but they probably didn't subtract that value from the starting value of the nitrous acid. And I put it in there because I felt that it was significant enough. And it comes out that it is significant enough. 4.5 times 10 to the negative 4, when you're working with very small quantities, is very different than 4.6 times 10 to the negative 4. So it's reasonable, because of the size of the H ion concentration, to subtract that value from the starting concentration of nitrous acid. It says, write the formula and name of the conjugate base of each Brønsted-Lowry acid. Now, to be clear, if you're going to have an acid and you want to make the conjugate base, what is left over when you remove a hydrogen? So whatever you're given, if you remove a hydrogen, then what's left over would be the conjugate base. For instance, if you have bicarbonate and you remove a hydrogen, then what's left over is the carbonate. So that will be the answer to this question. Clear? So it will be, the first one is bicarbonate. So if I remove a hydrogen, what's left over is carbonate. So that's going to be the conjugate base, the carbonate ion. Now, just to be clear again, you remove a hydrogen, what's left over, that's the conjugate base. And that would be hydroiodic acid. If you remove a hydrogen, you have iodide ion. Because you had hydroiodic acid, you remove an H, you're left with the iodide ion, that's the base. If you remove an H from ammonium, you're left with ammonia. And that is indeed a base. We know that's a base from our studies so far. So you remove a hydrogen, what's left over? And there's a similar rule when you're talking about, and this will be the bisulfite ion. There's a similar rule when you're talking about a base and the conjugate acid. Okay, so that will be the bisulfite ion. Next, calculate the OH or pH of each solution. So the pH is given, so the POH is going to be 14 minus 4.6, which would be 4.94. Then the negative log of 9.4 would be the concentration. So you're going to raise it to the power of 10 to the x, and you're going to put the negative on the other side, so it'll be negative 9.4, and then raise that to 10 to the x, and then hit equals, and that's it. So it's really a matter of, do you know how to use a calculator? So let's see what happens. I'm still here. So raise both sides to 10 to the x, so it will be the hydroxide ion concentration equals, hit equals now, (4 times 10 to the negative 10th). So that's going to be the hydroxide ion concentration. Now you want to do the pH. I'm going to let this play and see if you can do it before the answer is shown. Now you have a pH of 9.3, and what's going to be the hydroxide ion concentration. We're going to go through the same steps we did in A. See if you can do it. This is actually good practice for logs and 10 to the x, going back and forth. And 2 times 10 to the negative 5th molar. Okay, and then finally, D, so you're going to find the POH, or you could actually say 1 times 10 to the negative 14 divided by 7.3 times 10 to the negative 9th molar equals the H ion concentration. And then you could say the negative log of the H ion concentration. Or you can do it this way and find the POH first, which is going to be 8.14, and then find the hydroxide concentration from that. I, for some reason, had some arrows there, so just ignore the man behind the curtain there. So that's going to be 5.86. Okay, write the 3 equations for the stepwise ionization of phosphoric acid. So there's the first one. Then you're going to take the dihydrogen phosphate and do the next one, and it'll be hydrogen phosphate, and then the third one will be just the phosphate ion. Okay? Let's take a break. You'll never know I was gone. Use the Brønsted-Lowry and Lewis definitions of acids and bases to identify each reactant as an acid or a base. Well, I hope you can do this one. It would be KOH is the base and HBr is the acid. That's potassium hydroxide and hydrobromic acid. So, and that's what the answer says. And that salt will be neutral. This would be hydrochloric acid is obviously the acid. So, as a result, the base has to be the other one, and that would be the water. So if you know one of them, then the other one is the opposite, if you're unsure about water being a base. Write the formula for the conjugate base of each acid. This is a good one. I like this one. Write the formula for the conjugate base. So the conjugate base would be hydrogen sulfate, right? -1 charge, is that correct? And that is correct. Do you see why that's true? If it gives up one H, when it becomes an acid, consider it to be one proton at a time. So that would be hydroxide. If you give up one hydrogen, it would be hydroxide. Okay, and then what's next? Then hydrocyanic, or just cyanic acid would be the cyanide ion. And then I think that might be it. Let's see. D would be ammonium, and then ammonia would be the conjugate base to that acid. If you give up a hydrogen, you're left with NH3. And I think that might be it. Yes. Use the phosphate buffer to illustrate how a buffer system works. Show by means of equations how the pH of a solution can be kept almost constant when small amounts of the acid or base are added. So that's the dihydrogen phosphate, hydrogen phosphate buffer system. So the idea is if it's an acid buffer system, what you're going to do is you're going to add a base to it. You're going to add a base to the dihydrogen phosphate, and then what will happen is you'll take that OH, hydroxide, and you'll put a proton on it. It'll become water, so you'll get rid of that base. It will soak up the base, and you'll create the hydrogen phosphate as a result. So that's why it's a buffer system, because if you add, it's a weak acid, and if you add, so it's not going to be very acidic, so if you add hydroxide to it, or through sodium hydroxide, whatever, you get rid of it, you decrease it. And the equation would be here. It would be the addition of hydroxide would produce water and hydrogen phosphate. Write an equation for the reaction of each antacid with hydrochloric acid. So an antacid is actually a base. It's a salt of a weak acid. So if I have magnesium hydroxide, that's the antacid, and I would produce magnesium chloride plus water. Remember, it's not necessarily a weak base, magnesium hydroxide. It's kind of a little bit of a conundrum there, but anyway. So that, and then the calcium carbonate would produce water, carbon dioxide, and calcium chloride, because the carbonic acid is a weak acid and will break down to the corresponding acid anhydride and water. Aluminum hydroxide will break down to aluminum chloride and water. So that's actually what happens with, but it's a little more complicated than that because it is a buffer system. How would the equilibrium between hydrochloric acid and hydrochloride ion be affected by the addition of each? Hydrochloric acid. So this is a buffer system, hypochlorite and hypochlorous acid, and it would shift to the left if you're adding HCl. It would shift to the left. If you're adding NaOH, it's going to add hydroxide, so you're going to shift it to the right. You're going to shift it to the right. And that's about it. I think there's only two of them. Let's see if there's a C here. This is based on Le Chatelier's principle. The following data were collected from the titration of 50 milliliters of ethanoic acid, acetic acid. Remember, acetic acid I prefer to call ethanoic acid acetic acid, and you'll see that later in the tape. Now, or if you didn't see it on the lecture. So let's take some time to look at the data. I'm increasing the volume by approximately anywhere from 15 to 9 to 1. I'm increasing the volume slowly as I get up near the end point here. And look at the pH changes, okay. The volume of NaOH, all right, very good. And the changes in pH. So now what I'm going to do is I'm going to graph this data. Okay, I'm going to graph this data, and we'll see what the graph looks like on the next slide. Always examine data before you graph it. Okay, now look at this. You see, when all of a sudden it went vertical. In other words, it was an instant change. So let's look at the straight portion of the line. You're kind of eyeballing this based on the graph. You're not necessarily doing calculations. So those are the straight line portions. Now take the midway of the straight line portion, and that's what it's going to be. So now read the left axis. So it's going to be 8.8, 8.9, 8.7, and it would be 8.8. Approximating the titration endpoint would be the middle of that vertical portion of the graph. And so when approximating the titration endpoint, you take the high and low of the completely vertical portion of it, and so in other words, you're going to find the vertical portion of the curve, and then you're going to estimate the upper and lower limits of the vertical line, and then what you're going to do is you're going to find the midpoint, find the average of the limits, okay, and same thing, and then you're going to read the y-axis for the endpoint of the titration. So to review A and the problem, it says, what is the pH at the endpoint of this titration? Well, we came up with 8.8, and the book says 8.73. A little tough to read that closely on a scale that's very, very cloudy. B is use figure 1912 to identify one or more indicators that could be used to determine the endpoint in this titration. So which ones would we use? Well, we said 8.8. So phenolphthalein would definitely be used, and the book says phenol red. That might be used, but it may not work. Okay, write an equation to show that an aqueous solution of sodium ethanoate will be basic, ethanoate, ethanoate. So that is going to cause the sodium acetate is going to cause the water to give up a hydrogen to form acetic acid, because acetic acid is a weak acid, so it wants to form. So then you'll be stuck with the hydroxide-ion as a result of that, which would make the solution basic, and we'll see more about that a little bit later. Okay, it says arrange these solutions in order of decreasing acidity. So you want the most acidic. So HCl looks like the most acidic. Ammonium chloride is acidic, but has a weak acid, so that would probably be next. Then sodium acetate would be next, and then sodium hydroxide. So B, C, D, A, I think. Is that right? What do you guys think? B, so that would be the most, hydrochloric acid. And then the most basic would be least, B, C, D. Yeah, that's right, B, C, D, A. So make sure that that makes sense to you. That looks correct to me. B, C, D, A. Next. The graph shows the number of millimoles, m mole of water formed by the drop-by-drop addition of 1 molar HCl to a 25 milliliter sample of NaOH of unknown concentration. Write an equation for the reaction. So that's pretty easy. And then it comes out to be about 18 millimoles of water. So that's 18 millimoles of water, or 0.018 moles of water. Now we want to figure out what the molarity is of the NaOH, estimate the concentration. Remember, there's going to be an estimation based on our reading of the graph. So now, what do we do next? Well, we know that the equation is going to be NaOH plus HCl yields NaCl plus H2O, and that the mole ratios among the products and reactants is going to be 1 to 1 to 1 to 1. So, if we know that there's 0.018 moles of water, there's going to be 0.018 moles of everything. So where we usually put the stoichiometric masses, we're going to put the moles of each. So there's going to be 0.018 moles of sodium hydroxide, of hydrochloric acid, of sodium chloride, and we already know of water. So that's what we're going to do. We're going to put the number of moles above each of the compounds. And now we have to estimate, well, what is the molarity of the sodium hydroxide? What is it? So let's look at the next part of it. Well, I know that when I titrated, I had 0.018 moles per 25 milliliters, and that's going to translate to 0.72 moles, and that's my estimation, 0.72 molar. Their estimation is going to be, hold it, 0.75 molar. Let's review this right now just for a moment. Let's review what we've done. It says the graph shows the number of millimoles of water formed by the drop-by-drop addition of 1 molar HCl to a 25 milliliter sample of sodium hydroxide. So it's the water formed. Well, the HCl plus the NaOH yields NaCl plus H2O, or HOH. And it's going to be, the mole ratios are going to be 1 to 1 to 1 to 1. So I have 18 millimoles, which is 0.018 moles. So I use 0.018 moles of sodium hydroxide, hydrochloric acid, sodium chloride, and water. Everything is 0.018. So when I determine, and I used HCl to do the titration, I used 25 milliliters of it. Well, the HCl is going to give 1 HCl per particle of NaOH because it's 1 to 1. So whatever molarity of HCl I use, that's the molarity of NaOH. And the number of HCl's in 1 molar HCl, 25 milliliters of that, is going to be the same as NaOH. So in reality, I have 0.018 moles of NaOH in 25 milliliters as well. So then what I do is I want to determine the molarity. So it's going to be 0.018 divided by 25 equals X over 1,000, and that would be 0.72 molar. And that's it. Arrhenius, Brønsted-Lowry, and Lewis all developed theories to explain acids and bases. Which theory is easiest for you to understand? For me, it's the Arrhenius. Students are likely to consider the Arrhenius theory the easiest to understand, and the Lewis theory the best because it is the most general. All three theories provide definitions and describe accepted behavior of a certain group of compounds. The Brønsted-Lowry theory includes a greater number of compounds than the Arrhenius theory because it is more general, and the Lewis theory includes the greatest number of compounds because it is the most general. The Arrhenius theory is, for a young student, it's going to be plus, H plus, or the hydronium and the OH. So that's, for a young chemistry student, the Arrhenius is probably the easiest. If you're into chemistry more seriously, then you need all three. How can all three theories be accepted by chemists? Well, each particular theory explains a unique set of circumstances, or can explain a unique set of circumstances. For instance, there is a boron trifluoride, could be either an acid or a base. If ammonia is reacting with it, what is boron trifluoride? So that's one of the problems that you should consider. Demonstrate the relationship pH plus pOH equals 14. Hint, use the expression for Kw. Well, let's examine this. I'm going to let this run a little bit. It says, because log A times B equals log A plus log B, easy. Okay, that's just a rule. Like you have exponent rules, well, you have log rules. That's one of the log rules. The product of two bases equals the log of each and the sum of them. And then, so you have Kw equals the H plus times the OH, and that equals that equals 1 times 10 to the negative 14. Taking the log of each concentration term gives the log of the H plus the log of the OH minus equals negative 14. Then multiply both sides by negative and then distribute it. You get negative log H plus negative log or minus negative log hydroxide equals 14. Actually, minus log hydroxide concentration equals 14, and then the pH plus the pOH equals 14. Easy stuff. So that is the demonstration where pH plus pOH equals 14. That's the derivation of that. Here is a graph which quantity might correspond to the y-axis on this graph. H plus, pH, OH, or pOH. I've changed the rest of the slides to the y-axis might correspond to H plus because HCl is a strong acid, and it's not a linear relationship between the log and the molarity of the HCl. I've changed the, let's do another one. The following equilibria are involved in the solubility of carbon dioxide in water. All right, easy. This is similar to the way our respiration works. If seawater is slightly alkaline, would you expect the concentration of dissolved CO2 to be higher or lower than in pure water? Well, think of Le Chatelier's principle, and CO2 concentration is higher in pure water. Less CO2 becomes carbonate because pure water does not have the OH negative ions needed to reduce the H plus concentration. I've changed the timings to 15 seconds for the rest of them, so we have some time to talk about each slide. Critique the accuracy of each of these statements. Indicators such as methyl red provide accurate and precise measurements of pH. I wouldn't say accurate and precise because you need a range, because the indicators such as methyl red, they determined a range of pH, so it would be false. It's when you think of an indicator, especially colored indicator, changes color, that determines a range of pH values. According to the Arrhenius definition of acids and bases, ammonia qualifies as a base. Well, no, it would be Brønsted-Lowry would make that false. The Arrhenius base dissociates to give hydroxide ions in aqueous solution. Ammonia does not do this. Ammonia is a Brønsted-Lowry base. It does make hydroxide ions form, but not because of the Arrhenius. The strength of an acid or base changes as its concentration changes. Well, no, concentration is different. You like to look at dissociation. It says false. Strength is a measure of dissociation or ionization, not concentration. So that's going to be a great question on the test tomorrow. So think of dissociation, not concentration. The hydrogen carbonate ion carbonic acid buffer system is an important buffer system in the blood. This system is represented by the following equation. So you have H2O plus CO2 yields carbonic acid, which then yields H plus bicarbonate. Okay, so the CO2 is produced in the cell through respiration. Explain how abnormal breathing patterns can lead to acid-base imbalances in the blood that are called respiration acidosis, abnormally low pH, and respiratory alkalosis, abnormally high pH. Too rapid and too deep breathing also lead to respiratory alkalosis. All right. So now what? We have to explain that. All right. Hyperventilation releases CO2, obviously. That's heavy breathing, like very fast. The equilibrium shift causes carbonic acid and H plus concentrations to decrease. The loss of H plus increases the basicity of the blood, and alkalosis results. Hypoventilation does not release enough CO2. The CO2 buildup increases the H2CO3, carbonic acid, and H plus concentrations. The H plus concentration increases the acidity of the blood, and acidosis results. Calculate the pH of a 0.01 molar solution of sodium cyanide, NaCN. The Kb of the cyanide polyatomic ion as an anion is 2.1 times 10 to the negative fifth. All right. So it's going to be 10.66. Very good, 10.66. So that's simply you want to find the OH concentration using a Kb expression, and then finding the POH, and then the pH using POH plus pH equals 14. Show that for any conjugate acid-base pair, Ka times Kb equals Kw. Okay, Ka times Kb. So we're going to write now the definitions for Ka and Kb. Those are the expressions. You see that the HA will cancel, the A minus, the anion will cancel, and you're left with the molar concentration of the H plus times the molar concentration of the OH minus is therefore going to equal Kw. So not only does Ka Kb equal Kw, but the molar concentration of H plus times the molar concentration of OH minus also equals Kw. All right. Very handy derivation. Right, now, what's next? 95. It says the Kw of water varies with temperature as indicated in the table. All right, so now we have Kw. Now, look at Kw, and you know that Kw equals H plus times OH minus. Find the pH of water for each temperature in the table. Use these data to prepare a graph. All right, well, we know that Kw equals the H ion and the OH ion, the product of the two. This is pure water, so the H ion and the OH ion are equal. Therefore, I could say that, well, if I take the square root of both sides, that's going to equal the H ion concentration. Easy, because they're equal, and take the square root of both sides. So the negative log of the square root of the Kw is what I'm given, is going to equal the pH. Look that over, make sure you understand that. So at 0 degrees, it's going to be the negative log of the square root of 1.137 times 10 to the negative 15, and that's going to equal 7.4721 at 0 degrees Celsius. Number 2, the pH equals negative log of the square root of 2.917 times 10 to the negative 15, and that equals the pH of 7.2675 at 10 degrees. Number 3, the pH equals the negative log of the square root of 6.807 times 10 to the negative 15, and that equals the pH 7.0835, and that's 20 degrees. Number 4, pH equals negative log the square root of 1.461 times 10 to the negative 14 equals the pH of 6.9165 at 30 degrees Celsius. Number 5 and 6 are listed there, and you can see what's happening to the pH as the temperature increases. The pH is decreasing. So hot water will tend to be a little bit more acidic. And so there are the pHs listed, and we have B, which is using your graph, estimate the pH of water at 5 degrees Celsius. So here's the graph I constructed on Excel, and I put in a trend line. I did that myself, very easy to do, and I now will answer B and C. Now it says, what's the pH at 5 degrees? So I'm going to extrapolate here, and I'm going to, at 5 degrees, it's going to go up and then connect, and then I'm going to go over to the y-axis, put a little dot there, and then I can read that, and that's going to say a pH of approximately 7.3, 7.4. Not quite 7.4, but fair enough. I'm not sure what I was thinking. Maybe that's what the book says. So anyway, 7.38, 7.39. And then it says to what temperature is the pH of water? Approximately 6.85. And so I'm going to go back to the graph, and I'm going to find I'm going to find again the pH 7.4 for B, and I'm going to go back to the graph, and I'm going to put in the value for 6.85. I kind of repeated that slide, my apologies. So I'm going to go to the graph, and I'm going to find the pH 6.85, and then I'm going to mark that on the graph. Okay, here we go. 6.85, so it's halfway between 6.9 and 6.8. I changed all the slides back to 15 seconds because I did it at 8 seconds, but I had to rush through everything. This way I can take my time. So 6.85, and then bring a line down. So it's going to be about, looks like 3.4, 34, 35 degrees Celsius. and difficult to read the graph when it's so small. It might be bigger when I actually make the YouTube video. So that reads 35 degrees Celsius, and that's what I have. So the temperature is 35 degrees Celsius, and that corresponds to 6.85, a pH of 6.85. So I'll just let this play out, and there's the summary, and we'll wait for the next one. All right, hold on, I have not gone away. In case you ripped this and made a podcast, an MP3. Okay, here's another one. Use the cyanate buffer, OCN -1 is cyanate, to illustrate how a buffer system works. Show by means of equations how the pH of a solution can be kept almost constant when small amounts of acid or base are added. Not a very complex problem. I put in the OH, and I produce cyanate and water. I take the cyanate and I put in an acid, and I produce the cyanic acid from the cyanate. So pretty straightforward. Suppose you slowly add 0.1 molar NaOH to 50 milliliters of 0.1 molar HCl. Everything is 1:1. What volume of NaOH must be added to the resulting solution to become neutral? I'd say 50 milliliters. That's pretty straightforward. Everything is 1:1 to 1:1. Something we didn't do this chapter, and that's called equivalence. When you do IB next year, if you do IB, they'll probably add equivalence to the mix. So the answer is the pH equals 7 when the H ion and the OH ion are equal, because HCl is a strong acid that supplies 1 hydrogen ion per formula unit, and the NaOH is a strong base that supplies 1 hydroxide ion per formula unit. H ion and OH ion are equal when equal volumes of solutions of the same molarity are combined. So it's going to be 50 milliliters of each. Why? Because you have the same molarity of each solution, and everything is 1:1. So it is not a problem. All right, so 50 milliliters of each will be used. What is the molarity of a H2SO4 sulfuric acid solution if 80 milliliters of the solution reacts completely with 0.424 grams of sodium carbonate? Well, there's the reaction. Remember that sodium carbonate is a weak acid, is the salt of a weak acid, and sulfuric acid is a strong acid. I'm going to produce carbonic acid, which is a weak acid, and it will turn to H2O plus CO2, and then you have the sodium sulfate. It would be a complete double displacement reaction. So the sulfate ion reacts with the sodium, and the carbonic acid, the H2, goes with the CO3, the carbonate. So you get H2O plus CO2 from the carbonic acid. Remember, this is a double replacement, and then you get the sodium sulfates. And then the carbonic acid will decompose into water and carbon dioxide. So that's the reaction that we're shooting for. All right, so there's the reaction, and we're going to put above the sulfuric acid and the sodium carbonate, we're going to put the stoichiometric masses, and those will be 98 for sulfuric acid and 106 for sodium carbonate. We haven't put in our error yet. That's just a typo on my part, but it shall appear momentarily. And then underneath the sodium carbonate, we will put 0.424 grams. So the first thing we have to do is we have to do a mass-mass calculation and determine the mass of sulfuric acid that was used to completely react with 0.424 grams of sodium carbonate. So my constant ratio is sodium carbonate over sulfuric acid, or 106 over 98, and that will be the constant numeric ratio, 106 over 98. And as you know, that will equal 0.424 over X for the mass of sulfuric acid. Now we're going to solve for X, and that will mean that I used 80 milliliters of sulfuric acid, and the mass in grams that was in that 80 milliliters was 0.392 grams of sulfuric acid. So I used 80 milliliters, and in that 80 milliliters was 0.392 grams of sulfuric acid. Now, that's what I have. Easy? Now, if I convert 0.392 grams of sulfuric acid to moles, I know how many moles of sulfuric acid I have per 80 milliliters of sulfuric acid solution. So that would give me the number of moles, and then I would set that equal to X over 1,000, because I know how many moles of sulfuric acid once I convert 0.392 grams to moles. So why don't we do that first, and then we'll talk. Okay, so 0.392 grams of sulfuric acid, and I'm going to convert that to moles. So moles equals 0.392 grams times the ratio of 1 mole over 98. The grams cancel. That's how you know which way to put the ratio. Because what is it you want to cancel? The G's cancel. And I'm left with 0.392 divided by 98. And that's going to equal something fairly small. And that will equal, wait for it, 0.004 moles. So there are 0.004 moles of sulfuric acid in 80 milliliters. All right, well, how many moles are there in 1,000 milliliters? Once I determine the number of moles, here we go, here's the equation. Once I determine the X moles in 1,000 milliliters, you could just change that to molarity. So the number of moles in 1,000 milliliters is the molarity of the solution. Because remember, it's 80 milliliters of that solution. And molarity is volume of solution. So let's begin again. So 0.392 grams of sulfuric acid over 80 milliliters is going to be equivalent to 0.004 moles over 80 milliliters equals X over 1,000. Solve for X, and X will be, wait for it, 0.05 moles. Or the molarity will be a 0.05 molar solution of sulfuric acid. That was what I used, 0.05 molar solution of sulfuric acid. Fairly straightforward. Now, the last problem. Here we go. Wait for it. Household bleach is a solution of sodium hypochlorite. It is considered a hazardous solution because it is basic and because it contains the active bleaching ingredient hypochlorite. What is the hydroxide-ion molar concentration in an aqueous solution that is 5% sodium hypochlorite by mass? What is the pH of the solution? The density of the solution is 1 gram per milliliter, and the Ka, not Kb, be careful, the Ka is 3.5 times 10 to the negative 8th. So it's a 5% solution, which means 5 grams over 100 grams of solution. So it's going to be 50 grams of sodium hypochlorite over 1,000 grams of solution. That makes sense. Multiply it by 10 over 10, which is 1, so you haven't lost the integrity of the original ratio. So I know that 1,000 grams is 1,000 milliliters because the density is 1 gram per milliliter. That's easy. So it's 50 grams of sodium hypochlorite per 1,000 milliliters of solution. So what I've got is a ratio, and if I can figure out the number of moles is 50 grams of sodium hypochlorite, I'll be halfway there. So I need to find the molarity. Well, let's take a break for a moment and find the Kb. We have the Ka. Let's find the Kb before we go and find the molarity of the 5% solution of sodium hypochlorite. All right, I know Kb equals Kw over Ka. Therefore, it's going to be 1 times 10 to the negative 14 divided by what the Ka was, which is 3.5 times 10 to the negative 8th. That gives you 2.857 times 10 to the negative 7th, which is the Kb. You can see the Ka is 3.5 times 10 to the negative 8th, and Kb is times 10 to the negative 7th. So you can see quite clearly that those numbers are very small. That's going to be important later on. So 50 grams of sodium hypochlorite over 1,000 milliliters of solution, and I'm going to find the molarity now. So I want to divide by 74.4 grams. That's the atomic weight of one formula unit of sodium hypochlorite. Grams cancel, and I'm left with 50 over 74.4, about 2/3. So it'll be 67, 68, something of that nature. And it'll be 0.672. Good, because 50 over 74 is going to be about 0.66-ish. So 0.672 sounds about right. Right. So it's going to be 0.672 molar solution of sodium hypochlorite. All right, now what's next? Let's set up our dissociation equation that will plug in. Kb equals the molar concentration of hypochlorous acid times the molar concentration of the hydroxide ion divided by the molar concentration of the hypochlorite ion. Remember, the hypochlorous acid and the hydroxide ion are equal. So the numerator, I can say hydroxide times hydroxide, or x squared, easy, over the hypochlorite ion. And therefore, when I plug in, I know I don't have to subtract off. I don't know if you remember, if you have this as being ionized, right? So, and I produce some hydroxide, right? Well, for every one hypochlorous unit I dissociate, I'm going to make one of each. I'm sorry, every hypochlorite ion, I add a H2, I'm going to produce one hydroxide ion. So it's going to be 1 to 1. Well, for every the mass that you're going to subtract from the hypochlorite ion is so small because the Kb is so small. So you don't really have to subtract it. Let me go over that again and make that a little clearer. All right, look at the expression. The hypochlorite ion is going to be the reactant, and the chlorous acid and the hydroxide ion are going to be the products. Right? So the hypochlorite ion is on the left, and the hypochlorous and the hydroxide is on the right. So for every hypochlorous unit I make one hydroxide, so it's 1 to 1. So I'm going to get rid of some hypochlorite, correct? Okay. Well, I should subtract off, so the denominator shouldn't be 0.672. It'll be 0.672 minus whatever I produced relative to the hydroxide and the hypochlorous acid. Well, the amount that I produce is so small. Why do you know that? Because look, Kb is going to be times 10 to the negative 7. So it's going to be so small that it really doesn't matter. You know, it's going to be like 10 millionths place, so it doesn't matter. So you don't really have to subtract it off. So if that makes it, you know, because 10 to the negative 7th is 10 millionths. And in terms of precision, going back to chapter 3, it really doesn't matter. So you can just simply say hydroxide squared divided by the anion concentration. All right, so here the hypochlorous and the hydroxides are the same. Those molar concentrations are equal. Therefore, I could say that I have hydroxide squared in the numerator, and then the hypochlorite ion is in the denominator. That's actually the reactant, given what we're doing here. And then I can say that, okay, Kb is going to be 2.857 times 10 to the negative 7th. The hypochlorite ion is 0.672. Solve for OH minus. And so I'm going to multiply 2.857 times 10 to the negative 7th times 0.672 and take the square root. Now, Kb is very small, so the molarity of the reaction does not have to be subtracted from. All right, the molarity of the reactant. So that makes things a lot easier. Okay, now, what's left? So what we have is what we have to reduce. We want to solve for the hydroxide ion concentration, so we're going to multiply 2.857 times 10 to the negative 7th times 0.672, take the square root, and we get 4.4 times 10 to the negative 4 molar. 4.4 times 10 to the negative 4 molar. Now, what we have to do is we have to find the pOH. The pOH is going to be the negative log of the hydroxide ion concentration. Then what we'll do is we'll say 14 minus the pOH is going to equal the pH. That's where we're going with this. Okay, so the pOH equals the negative log of 4.4 times 10 to the negative 4 molar concentration, and then that's going to be approximately 3.36. So 3.36. Now, before it comes up on the screen, see if you can find the pH given 3.36 for the pOH. I'm still here. pOH plus pH equals 14. Plug in for the pOH. Solve for pH. pH equals 14 minus 3.36, and that's going to equal 10.64. 10.64, so that's the pH. And so the hydroxide ion concentration is 4.4 times 10 to the negative 4 molar, and the pH is going to be 10.64, and that concludes the book problems for the chapter on acid-base chemistry. Have a great day. Good luck on your test tomorrow. This is a revised edition, and take care.